Please work. So, Exam 2, Unit 2, Key from 2019. First couple questions are easy type questions. So you have to be able to rank the substituent. So you cut the alkene in half and be careful to not rank those higher. You go one bond out at a time. This carbon is bonded to a carbon, 2 hydrogens. This carbon is bonded to 2 carbons and a hydrogen. So actually this wins. It doesn't matter what's out here. Same idea here. Carbon, carbon, tie. Carbon, carbon, still a tie. Or, well, it's carbon and 2 hydrogens. So is this. Tied. Carbon to oxygen and 2 hydrogens. Carbon to carbon, carbon and carbon. It's not about total. It's just about the high element wins. So this is higher ranked, so it's E. Another one. Loop here is that these are the same, so you can't rank them. So it's neither. So for this one, draw an enantiomer and diastereomer. Easiest way to do this, enantiomer is everything is opposite. You could do the mirror image way as well, but whatever is wedged becomes hatched. And that's the enantiomer. It changes every asymmetric center. Diastereomer, here's just one example. At least one is the same and one is different. So this is the different one, and this is different. This is the same. So this is one possible diastereomer. There's lots of possible ones. Moving down, determine constitutional isomers. Enantiomers, diastereomers are identical. This is identical. Newton projection, just rotate, you can get the same thing. Diastereomers, one asymmetric center is the same, one is different. On a ring, on a chair, this is up, this is down, so it's like wedged and hatched. So you can see that one is the same and one is different. So diastereomers. Constitutional, same molecular formula, different bonding. Enantiomers, here's an example showing the mirror image, like they're like mirrors of each other. You could always do R and S with your moles if you wanted to. Those are enantiomers. This one's super tough, probably too tough. These are actually identical. So I'm not sure that's a bad question. Rank these, the reactivity of the leaving group. So be careful. Highest reactive one would be 4. Lowest is 1. Look at the relationship between these. So they're all would be tertiary, but phosphorus, silicon, sulfur, and chlorine are on the same row of the periodic table. So what changes as you go across a row is electronegativity. The more electronegative element will be able to stabilize, having a negative charge, disperse the charge better. So that's why chlorine's the best, silicon's the worst. So it's just literally going across the periodic table to answer that one. 5 is a pretty complicated problem. So the first part, just draw on all the beta hydrogens. So there's 6, 7 total, 2 types. These 2 products. Which product is a thermodynamic product? That's the more substituted product because of Zaitsev. Right. So that'll be the thermodynamic product, and it's also stabilized by hyperconjugation because it's more substituted. That's Zaitsev's rule. And thermodynamic product means the more stable product. So you gotta know that. So assume your thermodynamic product is also your kinetic product. So that means your thermodynamic product, if it's the kinetic product, it comes from the lowest activation energy. It's the lowest hill. That's what kinetics looks at. And then finally, I say it's the thermodynamic product. They both are. Or endothermic product, sorry. So that means in relation to the starting material, both products are higher in energy. So a lot of things. Endothermic, both products are higher energy than the starting material. Thermodynamic means the lower energy product of the two. Kinetic product means it comes from the lowest activation energy hill. And then to fill in the box, that would give the Z product only. Because this is a tertiary alkyl halide, I don't want a big reactive base. I actually want a small one, because if I had a big one, it'd be harder to get to this H because of sterics, and that would lead to the Y. So I need a small reactive base in this case to get just the Z. Last question, draw the molecular orbital picture for E2. The last question for this page. Really looking to see, did you remember that why things need to be anti-periplanar is because you need sigma star from the carbon leaving group bond to be lined up with the CH bond. That's why it has to be anti-periplanar. So I want you to see that this is showing that new pi bond being formed. Number 7, show the ring flip for each first. I should have wrote that first. So I wanted you to do the ring flip. So I want to see if you can still do ring flips. Then I want you to show the mechanism. Notice I told you it was E2 or SN1. So it tells you what I want. Reactive bulky base. I should have maybe not made this bulky. We're going to lead to what H's are anti-periplanar. So in this case, there's an H here that's down and an H here that's down. This is only a secondary alkyl halide, so we'll still make the Zaitsev more substituted product. 3 arrows, grab the H, CH sigma bond breaks, same time the carbon-chlorine bond breaks. Very similar to what we just looked at in the last question. See that anti-periplanar E2 reaction. And you go for the more substituted one. But again, be careful these chair ones. It has to be anti-periplanar for it to work. We worked on one in class where it wasn't, and so it didn't lead to the more substituted product. So you still have to have it be anti-periplanar. This one's a little simpler. Again, you gotta do the ring flip, but because it's SN1, you're gonna form a carbocation, which means, right, that's flat. The nucleophile comes from either the top or from the bottom. You get a racemic mixture if it's asymmetric center. It's not here, so it doesn't matter. Again, one of the things I always see is folks forget the methyl off that nitrogen. It just disappears. So make sure you don't lose that. Leaving group leaves, nucleophile reacts, and there's a deprotonation step, and there's also be HBr here too as well. Number 8, key here is another E2 reaction, telling you it's elimination reactive nucleophile, so it's not going to be SN2. Wedges and hatches, you need to draw a Newman projection. So draw a Newman projection, this eclipsed. You need to get the H on carbon 2 and the bromine on carbon 1 anti-periplanar because they're going to do an E2. So they need to be 180 degrees apart. So you rotate that. Once you do that, that'll help you know on the new pi bond who's on the same side, who's cis and who's trans to each other. Be careful, it's not this H that comes off, it's this H, right? Don't confuse the alpha H with the beta hydrogens, okay? There's only one beta hydrogen here, so that's the one that needs to go. Get them anti-periplanar. Draw your pi bond. On carbon 1 here, it has the torpedo and the hydrogen. And then if I'm dividing this in half, right, if I'm taking this, I can see that this tert butyl is on the same side as this methyl. So there will be cis, and this H and this vinyl group are on the same side. That's the other key piece, is drawing this alkene correctly. So, multiple choice questions. Careful to read these. Circle the molecule below that will not undergo an E1 reaction. So you think of an E1 reaction, you should immediately think carbocations. So nothing primary. unless it's primary allylic or primary benzylic. So if you look at these, this is primary, but primary benzylic. This is primary, but primary allylic. So these will be stabilized carbocations because of resonance, right? Pi bond resonance. This is just primary. It can't be stabilized by anything but hyperconjugation and very little of it. This is tertiary, which can be stabilized by 1, 2, 3, 9 hyperconjugation buddies. So that'd be a little more stable. So the one that will not is this, because you'd have to make a primary carbocation. What type of reaction is shown below? So this is the NaBr. You need to recognize that that's Na plus Br minus. So it's a reactive nucleophile. Right? Also polar aprotic solvent. Polar aprotic solvent. So you should be thinking SN2. Even if you didn't, you should look at the product and see the bromine here has exchanged out for this. And the way it's substituted, it went from the leaving group was hatched, the group you added is wedged. That should be a big clue. It's SN2 because you have inversion. C is a tough one. Knowing what a meso compound is, it has a mirror plane and it has asymmetric centers. This has a mirror plane but no asymmetric centers. This carbon is not bonded to 4 different things. This has asymmetric centers but no mirror plane. Has a mirror plane, but again, this carbon is not bonded to 4 different things. This one checks all the boxes, definitely has the mirror plane. This carbon is bonded to a methyl, a hydrogen, a CH2, and a CH. So it's bonded to 4 different things. So this is the meso compound. D, what's the slowest step? Not a carbocation rearrangement, not a nucleophilic attack, not beta hydride. First of all, it's an SN1. It's always going to be carbocation formation. That's always going to be the slow step for these SN1 or E1. All right. Indicate the type of reaction in the box below and give the major product. Use each type once. Not asking for mechanism arrows except for the last one. So it's not more work than you need to be. If you see all these, the electrophile is all secondary allylic. So that's not going to help us. Right, they're all secondary allylic. So that doesn't change. And that's possible. That works for SN1, SN2, E1, and E2. So we need to look at the nature of the nucleophile or base. So the first thing we ask ourselves, is it reactive? Meaning, does it have a negative charge? If it has a negative charge, that makes us think SN2 or E2. The nucleophile and base is involved in the rate law, the rate determining step for both those reactions. So that's why they're involved. Once we see the negative charge, we said E2 or SN2, then we look at the size of the nucleophile. So this one's large, so that makes me think E2, large and negative charge. I need to have things be antiperiplanar. I want beta hydrogens that are sp3 hybridized. So I would take these, not this one, and I would give a conjugated product. Again, I can do resonance. That's a good thing, right? Resonance always. Difference between these two, there's no charge. So this makes you think E1, again, not reactive, but large, less likely to do substitution. And I said you'd use each type once. So same product as E2, different mechanism, but same product. Last two, we're going to have non-reactive nucleophile, but it's small, so that makes me think SN1. Leaving group leaves, makes a carbocation that's flat, so the nucleophile could come from the top or the bottom, so it could be wedged or it could be hatched. And because this is an asymmetric center. It's sp3 hybridized, bond to 4 different things. Of course, there's a hydrogen there. We just don't draw it in. It's been there the whole time. You either need to draw it like this or draw both the wedged and the hatched version to indicate that you realize you're making a racemic mixture of both R and S there. In contrast, the SN2 is reactive, negative charge, small, but it's going to do inversion, so it's going to come from the backside to sigma star, and it's going to be wedged because the iodine is hatched, so it's going to come from the opposite side, and you only make one of these. You need to make sure you indicate that that's wedged. So just contrast the SN1 and E1. Same first step. Leaving group leaves. So you have a carbocation here. And you're just looking for beta hydrogens, but sp3 hybridized beta hydrogens. So really you only have one type, because this is sp2 hybridized, so you're not going to take that H. In this product, by taking these H's, you also make it conjugated. 2 pi bonds next to each other can do resonance, and that's going to be the more likely thing to happen. So same first step as SN1, but because this is large, substitution becomes less likely, and it's more likely to do an elimination, in an E1 in this case. All right. Couple of things for this one. Show the mechanism. Told you it's SN1. That should automatically make you think, I'm going to need to have a carbocation, probably rearrangements. I say number your carbons. So you got to do that. Bolded and underline in each step, right? Not just the first one and then all of a sudden something happens. And I said a hint, HCl gets regenerated in the last step. So you see catalysts are regenerated. So we did one like this where we had an alcohol. So this is not a good leaving group by itself. But if you protonate it, this is a protonation step. So we do a protonation. We've now made this like a water, a really good leaving group. And again, the numbering is just random, but you just need to be consistent. Leaving group leaves. All right. And what's going to happen, since you see the product, you should recognize this is a 5-member ring. All of a sudden now it's a 6-member ring. What happened? So the ring had to expand. So what happens here is the bond between 3 and 4, as I have it labeled, breaks. And those 2 electrons move to carbon 2. So now 4 and 2 are bonded. And 3 lost a bond. It has a plus charge. So I drew it kind of ugly here, right? To make it easier to see what happened. These 2 electrons in this bond left, and carbon 4 is now bonded to carbon 2 to make a 6-member ring, which is more stable for carbons. So there's this. Carbocation is now on 3. It lost a bond. So there's the ugly way to draw it, and then I drew it pretty too. Numbering is the key here. This is a secondary carbocation, so is this. But this is in a 6-member ring, which is more stable. Can we make it more stable than that? We actually can. And the reason I moved this carbon and not this H is because if I put a carbocation next to the sulfur, sulfur has lone pairs. It could do lone pair resonance. So the methyl shifts. The plus charge is tertiary. And I didn't show this, but it could do pi bond resonance. So it can have something that actually has a full octet, which would really be good. So that's why it shifts that way versus, right, you could think of a hydride shift perhaps moving there. So that's why that takes place. Besides the fact that's what the product looks like. So finally, after all these rearrangements, we're finally ready to do the nucleophile reacting. Right? So the oxygen goes there. These carbons are still on the oxygen. They're not going anywhere. And of course, racemic come from the top or the bottom. Bromine comes and takes the H, does the deprotonation, and that's what leads us to our product. And I think, wait a second, I changed it to bromine somewhere along the line. This should be a Cl, not a bromine. Whoops. And that's how you regenerate HCl at the end, the last step. So for this one, lone pairs, formal charges, mechanism arrows. I told you it's elimination. It's going to be an E1 just based on looking at the structures I had drawn for you. You form a carbocation. There's going to be some rearrangements. First step, leaving group leaves. Make sure you have your lone pairs on everything. Minus charge on the bromine, plus charge there. Secondary carbocation. So you only do rearrangements if you make something more stable. So there's a hydride shift to a secondary allylic carbocation, which is more stable than secondary because this can do resonance, which you need to show then. So it's secondary allylic. You do resonance to tertiary allylic, which is more stable than secondary, right? More substituted hyperconjugation. Get here, you need to eliminate an H, a beta hydrogen, right? Alpha, beta, 1, 2 bonds away. Just like all the elimination reactions. You could have done it from this one. Same, these methyls are the same. Do the E1 elimination, and there's your final product.